All right, so this next video is almost identical to the first video. Optimization without a closed and bounded interval is actually pretty similar. There's just going to be some small things that pop up. You just have to make sure that just a slight difference in how we verify that something is indeed a maximum or a minimum. So let's just jump right into example 6. We have a rectangular box with a square base and an open top and a specific volume that we're constructing. So let's start by drawing a picture. Rectangular box with a square base. The base is square. We can call it x by x. And an open top. So it kind of looks like this. Some height y, sure. And the volume is 216 inches cubed. What should the dimensions of the box be to minimize the surface area? We're trying to minimize the surface area of this open box. Well, there's no top, so it's just going to be, well, you know, what's the surface area at the bottom? And then add up the surface area of the four sides. I actually don't want to draw it that way. That's not super clear. All right, so the surface area is going to be the area of the bottom, which is x times x, plus the area of the four sides. Each side is going to have area x times y. And there's four sides. What is our domain? Well, it's kind of hard to see right now. All of them have to be positive. Let's wait on the domain for a bit. And again, even in the step-by-step instructions, it tells you, yeah, if you know the domain, put it in step 2. I think it was step 2, but otherwise you can wait until later. Because the volume is 216 inches cubed. Again, this right here is our objective function, what we're trying to minimize or maximize. And we know that the volume, so we could say subject to the constraint, that the volume is 216 inches cubed. But what is the volume? It's the area of the base times the height. So if we want to get our area function to have only one variable to substitute, let's solve for a variable in our constraint equation. Solving for y is probably the easiest, because now you can just plug that in to get an area formula. That's a function of only one variable. A is a function of x, and it's x squared plus 4x times y, which is 216 over x squared. So what's the biggest that x can be? What's the smallest that x can be? Well, the smallest that x can be is 0, but 0 is not included anymore. The area is not defined when x is equal to 0. Okay? This function doesn't even exist when x is equal to 0. What's the biggest x can be? And x really can be as big as we want. It's going to be a really, really flat box if x is really big. But x can actually go off to infinity. So it's actually just this. 0 is less than x. X is bigger than 0. That's our entire domain. So we don't have a closed and bounded domain anymore. It's unbounded and it's open on the other side. So that'll change a couple things. Let's simplify this area function first and then talk about how things are different. Our surface area is going to be x squared plus one of the x's cancels, and 4 times 216 is 864, I believe. So we're trying to minimize this function. So to find the global or absolute minimum of a function that's not on a closed and bounded interval, we just look at the limits and then look at the critical points. Remember, that was a short video that we talked about earlier. So what is the limit of this area function as x goes to infinity? Well, as x goes to infinity, Limit's coming back again. This term goes to 0. And this term goes to infinity. So as x approaches infinity, the area formula, the surface area, becomes infinitely big. Right? A really, really flat, infinitely tiny box, the surface area gets gigantic. Well, that's one end of the domain. Now we have to check the other end of the domain. As x goes to 0 from the right of the area function, well, that's kind of the opposite. Now, as x is going to 0 from the right, this goes to 0, and this goes to positive infinity. This is a reciprocal function from the right. Plug in 0.000001, you're going to get a very, very big answer. So this also goes off to infinity. So at each boundary, it's going off to infinity. There is no global maximum for the surface area function. So if we were asking what is the maximum surface area, we'd say there is no maximum surface area. We can make this surface area as big as we want. But there is going to be a minimum. And again, if one of these were a negative infinity, there would be no minimum because we could make it as small as we wanted. So because of this right here, because a limit is infinity, it means there's no global or absolute, again, we use those words interchangeably, max. But because it's a continuous function, there is a global min. We do have an absolute min. And we'll find that at the critical point. So look for a critical point. There are two, well, there's only one critical point. Let's take the derivative. Derivative with respect to x is 2x minus 864 over x squared. So this derivative does not exist when x is 0, but that's not in our domain anyway. So the only critical point is going to be when the derivative equals 0. Multiply both sides by the LCD to solve this equation. To get 0 equals 2x cubed minus 864. Those x squareds cancel on that second term when you distribute. Or 2x cubed equals 864. Divide both sides by 2 to get x cubed equals 432. Or x is approximately, because I don't think this is anything nice, the cubed root of 432. I don't need all of these anymore. That was a lot. Cubed root of 432. Cubed root is the same as an exponent of 1/3. About 7.560 inches. The 0 is meaningful. It is a significant figure here. We will include it. It's asking what are the dimensions of the box and what's the minimum surface area. So that's the x coordinate. The y coordinate, we said y was 216 over x squared. That's approximately equal to 216 over 7.560 squared. Calculate that out. 216 divided by this answer squared. We can square it by putting a 2 here. About 3.780. So the box has dimensions 7.560 inches by 3.780 inches for a minimum surface area of whatever the function result is. So normally, right, when we find absolute extrema, we have to plug all the numbers in before concluding that we have an absolute minimum or absolute maximum. Here, Because of that logic that's in red, I know this is an absolute minimum, but we do still have to plug it in to get the value. So our surface area equation is A is a function of x. It was x squared, sorry, was x squared plus 864 over x. So the area when x is about 7.560, area is about 171.4. inches squared. It's an area. And again, if you do look at the surface area formula, do look at this equation from, I don't know, 1 to 20 or something, and surface area is going to be pretty big. You can see that, yeah, as x gets really small, the surface area gets infinitely big. And as x gets really big, the surface area also gets infinitely big. The sweet spot is when x is about 7.56 inches for a surface area of 171.4 inches squared. You really can see that by checking your answer here. And that's all there is to these sorts of problems. Just watch out for those domains. We'll do an extra problem in the next video for more practice.